Imagine a genetic mutation that was, designed by nature to save your life from one of the absolute deadliest infectious diseases in the world.
Right. It does its job brilliantly at first. It literally keeps you alive.
Yeah, but then years later, that exact same biological defense mechanism slowly, almost silently, turns against you. It starts destroying your body's internal filtration system. Welcome to the deep dive.
Thanks for having me. And yeah, today we are looking at this really illuminating September 2022 literature review by the Institute for Life Sciences Collaboration.
Exactly. It's titled Sickle Cell Disease and the Effects on the Kidney. And it details pretty much everything from these microscopic cellular traffic jams to the actual standard of care in Ghana.
It is a remarkable piece of literature. I mean, the scope of it really forces you to completely shift your perspective on a disease that we've supposedly known about for over a century.
Right. So our mission today is to basically change how you, the listener, understand sickle cell disease, or SCD. Because when you picture genetic illness, you probably think of, I don't know, the obvious surface level symptoms.
Yeah, the visible pain crises, mostly.
But very few people realize there is this high-stakes battlefield deep inside the body, specifically in the kidneys. We're going to explore how that life-saving mutation becomes just a catastrophic liability.
And we'll look at how doctors accidentally cured a patient while trying to treat their cancer, which is a wild story.
Totally wild. And also why something as incredibly low-tech as a pen and a journal is actually like a frontline medical tool.
Okay, let's unpack this.
So to really grasp the damage happening to the kidneys, we first have to zoom out a bit and look at the blood itself.
Okay, lay it on us.
Sickle cell disease isn't some rare anomaly. It is actually the most common monogenic disorder globally. James B. Herrick first reported it in Western medicine back in 1910.
Wow, over 100 years ago.
Right. And our source notes that today, roughly 300,000 infants are born with sickle cell anemia every single year.
Okay, I always hear that term monogenic disorder. Just to make sure we're all on the same page, that means this entire massive cascade of health issues comes down to a flaw in just one single gene? Just one, yeah. It's a missense mutation in the beta-globin gene.
One gene? That's crazy.
At the cellular level, the body essentially substitutes a single amino acid valine, right, where should have placed a completely different one called glutamate.
Wait, how does one single amino acid swap cause a global health crisis? I mean, it sounds like a typo in a million-page book.
It really does.
Yeah.
But think about the chemical properties of those two amino acids. Glutamate loves water. It's hydrophilic.
Okay.
Valine, on the other hand, absolutely hates water. It's hydrophobic. And blood is obviously a very watery environment.
Right. It's mostly liquid.
So when you swap a water-loving building block for a water-hating one, the hemoglobin molecules literally panic. They want to hide that valine from the water. So they stick to each other, clump together, and form these long, rigid fibers.
Oh, wow. And this clustering of the mutation is geographically specific, too, which really blew my mind when I read the source.
Yeah, it's highly concentrated.
The review points out the highest prevalence is in sub-Saharan Africa, the Mediterranean basin, the Middle East, and India. The majority of births happen in Nigeria, the Democratic Republic of the Congo, and India. Why are those specific regions the epicenter of this water-hating amino acid typo?
What's fascinating here is the evolutionary context, The clustering is anything but random. Carrying the sickle cell trait provides a really notable level of protection against severe malaria.
Oh, right, because of mosquitoes in those regions.
Exactly.
Yeah.
If you look at a map of historical malaria endemicity and you overlay a map of the sickle cell gene, they match almost perfectly.
That is wild.
In regions where malaria was just devastating populations, curing this genetic typo is kind of an evolutionary superpower. It helped people survive childhood.
Wait. I'm trying to wrap my head around this. This devastating, painful disease is fundamentally an evolutionary defense mechanism that just went way too far.
Yeah. Nature is all about trade-offs, right? If you inherit the mutated gene from just one parent, you possess the trait.
So you get the superpower.
Right. You get the malaria protection with very few health complications.
Right.
The real tragedy occurs when you inherit the gene from both parents. Then you don't just get the trait, you get sickle cell disease.
And that brings us back to those long, rigid fibers forming in the blood. Let's try to visualize this for anyone listening who might not be, a cellular biologist.
Sure. Helps to picture it.
Healthy hemoglobin in our red blood cells acts kind of like a sponge. It changes shape to release carbon dioxide, picks up oxygen, and then bounces right back to its normal plump shape.
It's very squishy, yeah.
But with this mutation, when the cells enter a deoxygenated environment, say, like right after they've delivered their oxygen to your leg muscles, the hemoglobin polymerizes.
Right, they stiffen up completely. The cells lose all their natural elasticity, and they distort into that famous crescent or sickle shape.
So if healthy red blood cells are like flexible, rubbery delivery trucks navigating the really tight alleys of our capillaries.
Bending and folding through microscopic spaces.
Exactly. But under low oxygen, this mutation suddenly turns those flexible trucks into rigid, elongated logs. I'd imagine a bunch of rigid logs trying to squeeze through a tiny alley causes a massive biological traffic jam.
That's exactly what happens. It causes total gridlock. The medical term for this is a vaso-occlusive crisis.
Yikes. That sounds painful.
It is. But the logs don't just block traffic, they're incredibly fragile. They suffer from hemolysis.
Which
Means they physically rupture, they literally break apart inside the bloodstream.
Oh man, I'm assuming red blood cells just exploding in your veins is really bad news for the surrounding tissue.
It sets off this systemic chain reaction. First, you get tissue ischemia.
Mhm.
The surrounding tissue is starved of oxygen because, well, the delivery trucks aren't getting through.
Right.
But more insidiously, the ruptured cells spill their inner contents directly into the blood, and that violently consumes the body's supply of nitric oxide.
Wait, I know nitric oxide is popular in like fitness supplements for the pump. Doesn't it keep your blood vessels relaxed and wide open?
That is its primary job, yes. So when hemolysis just depletes all your nitric oxide, your blood vessels violently constrict.
No.
Yeah, and the delicate lining of the vessels gets severely damaged. This widespread endothelial dysfunction is really the root cause of the severe cascading problems you see in sickle cell patients.
Like the chronic leg ulcers and pulmonary hypertension.
Exactly, and debilitating strokes. The entire circulatory highway system basically begins to break down.
Well, if the highway system is breaking down, then the destination processing all that traffic is going to take an absolute beating.
For sure.
And that naturally brings us to the specific organ that bears the absolute brunt of this damage, the kidneys. I mean, they are our filtration system. They are incredibly vascular, meaning they're just packed with tiny blood vessels, so they are constantly forced to process these rigid, sickled logs.
And the kidneys present a uniquely hostile environment for sickle cell blood. The inner core of the kidney, the renal medulla, functions by being hypertonic.
Hypertonic, meaning very salty.
Right. It has a very high concentration of salt to help draw water out of your urine. And because of how it functions, it is also relatively hypoxic.
Wait, meaning it naturally operates with very little oxygen?
Exactly. Very low oxygen.
Hold on. Salty and low oxygen.
Yeah.
You just said low oxygen is the exact trigger that causes the red blood cells to turn into rigid logs. It's like the kidney is accidentally a sickle cell manufacturing plant just by doing its normal everyday job.
I know, the irony is brutal. The kidney's natural environment practically guarantees the blood will sickle while passing through it.
That's just unfair.
It really is. This leads to a condition called sickle cell nephropathy, or SCN. It damages the entire length of the kidney's microscopic filtering units, the nephrons. But the disease operates on a very deceptive timeline, especially in kids.
Yeah, the childhood phase described in the source is wild. In the early stages of life, young patients actually experience increased renal blood flow. They have a higher glomerular filtration rate. It's called hyperfiltration. But why would a damaged kidney filter faster?
Basically, the body is desperately trying to compensate. Because the red blood cells keep rupturing, the child is chronically anemic.
So the body thinks it's suffocating.
Exactly. The body senses the low oxygen levels and thinks we need to circulate blood faster to deliver enough oxygen. So it dilates the blood vessels feeding the kidneys.
Oh, I see.
The kidneys are suddenly flooded with massive amounts of blood, forcing them to work overtime.
It sounds like running a car engine in the red zone for years on end. If you only look at the speedometer, it looks like the engine is performing incredibly well. It's generating all this power. But internally, you're just burning out the pistons.
That's a perfect way to put it. That hyperfiltration physically stretches and stresses the filtering membranes. Eventually, the structural integrity just gives way.
So it can't keep up the act forever.
Right. The childhood hyperfiltration inevitably subsides, drops to a quote-unquote normal rate, and then, as the patient reaches adulthood, it plummets to subnormal levels.
The engine burns out.
The engine burns out. And this trajectory leads directly to chronic kidney disease, or CKD. The review states that CKD occurs in more than half of all adults living with sickle cell disease.
Over half. I mean, that is staggering. And the physical manifestations of this decline are alarming. The text discusses hematuria, massive bleeding, with clots actually showing up in the urine.
It's terrifying for patients.
I can imagine. And that's happening because the sickled cells are literally blocking blood flow deep inside the renal medulla, right? Starving the kidney tissue itself of oxygen.
Yeah, that starvation is called medullary ischemia, and it leads to papillary necrosis. Parts of the kidney tissue simply die and slough off into the urinary tract.
The reality of this progression is just incredibly grim because for patients who progress all the way to end-stage renal disease, meaning they require dialysis or a kidney transplant just to survive, the review notes a 26% mortality rate within the very first year of starting renal replacement therapy.
A 26% mortality rate in year 1 tells us that waiting for end-stage failure is essentially a death sentence.
It really is.
Which raises an important question. If the end game is that devastating, how do we intervene earlier? The problem is, early sickle cell nephropathy is notoriously silent.
Because of the hyperfiltration making things look normal.
Exactly. The routine tests doctors use to check kidney function often appear completely normal during that childhood phase. By the time the standard tests finally show a problem, the kidney is already permanently scarred.
So the medical field is basically flying blind until it's almost too late. We need early warning flags, like to spot the damage while the engine is still running hot. The source highlights a massive push to find novel biomarkers in the blood or urine.
Yeah, researchers are hunting for molecules that signal microscopic kidney distress years before traditional creatinine tests would ever catch it.
What kind of markers?
One major focus is serum SFLT1. Elevated levels of this marker seem directly linked to the development of albuminuria, which is when the damaged kidney filters start leaking protein into the urine.
Oh, gotcha. Another marker mentioned in the source is plasma pentosiodine. What actually is pentosiodine? The text says it detects moderate renal failure earlier, but how does it work?
Pentosiodine is what we call an advanced glycation end product. Essentially, it's a marker of oxidative stress and protein damage in the body.
Okay.
Healthy kidneys clear it out of the blood and just dump it into the urine. But if plasma levels of pentosiodine start rising in the blood, it's an early, very sensitive alarm bell that the kidney's clearing mechanism is beginning to stall out.
Okay, so let's say we get better at spotting it. The alarm bell rings early. What weapons do doctors actually have to fight back at that point?
Curiously enough, one of the most effective tools for managing this specific kidney damage is a very common class of blood pressure medications called ACE inhibitors.
Wait, a standard blood pressure pill. How does lowering overall blood pressure stop the sickle cells from destroying the kidney?
Well, it actually lowers the pressure inside the kidney's specific filtering units.
Oh, I see.
By dilating the blood vessels that exit the filter, ACE inhibitors reduce that dangerous hyperfiltration pressure we talked about. The source notes that a brief course of these drugs can decrease protein leakage by over 60%.
That's huge.
And in pediatric cases, a specific ACE inhibitor called enalapril resolved microalbuminuria completely in 56% of patients.
Wow, so it's really buying the kidney's precious time. And I read doctors also use erythropoietin-stimulating agents to tell the bone marrow to produce more red blood cells, which fights the severe anemia.
Right.
But as amazing as these tools are, they are really just managing the decline. They aren't a cure.
True, but there is a curative option. Hematopoietic stem cell transplantation, or HSCT. In everyday terms, a bone marrow transplant.
Oh, and the historical footnote in the source of how this was discovered is just fascinating.
That's one of my favorite medical stories.
I love this story. So, the first patient ever cured of sickle cell disease received this transplant back in 1984, but the doctors weren't even trying to cure their sickle cell.
No, not at all. The patient actually had acute myeloid leukemia.
Yeah.
So to save their life from the cancer, doctors had to completely eradicate the patient's bone marrow using heavy radiation and chemotherapy.
And then they replace it with donor marrow.
Exactly.
Because the bone marrow is the factory that produces red blood cells, they essentially demolished the factory producing the mutated sickle cells and replaced it with a donor factory that produced healthy, flexible delivery trucks.
Right. Curing the sickle cell disease was a completely unanticipated, completely accidental outcome of the cancer treatment.
A miraculous accident. But obviously, bone marrow transplants are perilous. They require a matched donor, they carry severe risks of rejection, and the chemotherapy required is highly toxic.
Very toxic. They are generally reserved for patients suffering from extreme life-threatening complications.
So for the broader population, what's the alternative? The review points to a true pharmacological game changer, hydroxyurea.
Yes, hydroxyurea is massive.
The review heavily praises it. It stabilizes declining renal function and can apparently cut the frequency of painful crisis episodes right in half. But the source refers to it as a myelosuppressive agent.
Right.
Hold on. Myelosuppressive, meaning it actively suppresses the bone marrow from doing its job. Why on earth would you want to suppress the marrow in a patient who is already severely anemic and desperately needs blood cells?
I know, it seems completely counterintuitive, but sickle cell disease isn't just about the red blood cells.
What else is involved?
The bone marrow is also pumping out certain white blood cells, specifically neutrophils, and immature red blood cells called reticulocytes. And these cells are incredibly sticky.
Sticky.
Yeah, they attach to the lining of the blood vessels, acting like glue that catches the sickled red blood cells. That's what actually creates those traffic jams.
Oh, so hydroxyurea suppresses the marrow just enough to lower the production of those sticky cells, making the blood vessel wall slippery again.
Exactly. But here's where it gets really interesting.
Yeah, because the drug has a second, even more amazing mechanism, right? The source explains that hydroxyurea increases the body's synthesis of something called fetal hemoglobin.
Yes.
Are we essentially chemically tricking the adult body into thinking it's still in the womb?
If we connect this to the bigger picture, that is the exact biological loophole we're exploiting here.
That is so cool.
Before we are born, we obviously don't breathe air. We get our oxygen through the placenta. So human fetuses produce a special type of hemoglobin HbF that binds to oxygen much more aggressively than adult hemoglobin does.
And crucially, the fetal hemoglobin gene doesn't contain the sickle mutation.
Bingo. By chemically reviving the body's dormant ability to produce fetal hemoglobin alongside the adult hemoglobin, hydroxyurea prevents the cells from polymerizing.
The fetal hemoglobin physically interrupts the rigid fibers from forming.
Exactly. It gets in the way of the clump.
Okay, so we have bone marrow transplants, we have womb-tricking drugs, we have ACE inhibitors. The science is just incredible. But if all of this exists, why are we still seeing things like a 26% mortality rate for kidney failure?
That's the real tragedy here.
It brings us to the frustrating reality of geography, infrastructure, and standard of care. Because the literature review draws a very sharp contrast between the survival rates in rural areas versus a highly structured, comprehensive care model in Ghana.
I mean, the disparity is just profound. The source explicitly points out that chronic kidney disease patients in rural settings suffer significantly higher mortality, morbidity, and hospitalization rates.
Well, that's heartbreaking.
You can have the most advanced biomarkers in a laboratory, but if the patient lives 100 miles from a clinic, those biomarkers are useless.
It really comes down to things we completely take for granted. Lack of transportation, a severe shortage of nephrologists in rural areas, and crucially, a lack of allied health professionals, social workers, community health workers, dietitians. The level of care a patient receives is often dictated entirely by the financing source available in their zip code.
And you contrast that rural fragmentation with the standard of care in Ghana, which is detailed in the review by Ra Ankomete from the University of Ghana Medical School.
It sounds like a masterclass in holistic medicine.
It really is.
Yeah.
It's a multidisciplinary model that treats the entire human being, recognizing that a biological traffic jam affects literally every aspect of a person's life.
Their approach to pain management is a perfect example of this. A vaso-occlusive crisis is described in the text as excruciating, bone-crushing pain. The instinct in many Western hospitals is to immediately administer heavy intravenous opiates.
Give them the strong stuff, right?
Yeah, but the Ghana model deliberately minimizes opiates.
They focus heavily on resolving the underlying physical block rather than just masking the pain response. They utilize non-steroidal anti-inflammatory medications, acetaminophen, and above all, intense hydration.
So they're flooding the body with fluids to literally expand the blood vessels and wash the traffic jam away.
Exactly. Flush it out.
They also prioritize prophylactic penicillin and strict immunization schedules. They recognize that a simple bacterial infection can cause a fever, which causes dehydration, which then triggers a sickle crisis.
It's all connected. But the medical interventions are just the foundation there. The Ghana model integrates nutritional support, like supplementing with folic acid.
Right.
It also mandates psychotherapy to help patients cope with the chronic anxiety of living with such an unpredictable, painful disease.
Yeah.
They have physiotherapy for joint damage, peer parent support groups.
And they even coordinate job training and vocational services, which is amazing.
They realize that if a patient loses their job because they were in the hospital for 2 weeks, The stress and poverty will just trigger another hospital visit.
They basically build a social fortress around the patient. But out of all these interventions, the source states something that honestly shocked me. It says that self-management is the single most significant factor influencing a patient's life.
Oh, absolutely. Because medicine isn't confined to a hospital ward. For a chronic genetic condition, health is determined by the hundreds of small choices a patient makes at home every single day.
The text specifically elevates the importance of keeping a daily journal. I was struggling to understand this at first. For a patient with a complex hematological disorder, a notebook and a pen are considered almost as crucial as a prescription pad.
Think about the mechanics of the disease we've been talking about. A crisis is triggered by subtle shifts in the body, slight dehydration, a sudden drop in temperature, mild overexertion, hidden emotional stress.
Right.
By meticulously tracking their daily habits, food intake, physical activity, and early symptoms of fatigue in a journal, the patient maps out their unique triggers.
Oh, so they basically become their own early warning diagnostic system. If they notice that every time they drink less than 2 liters of water and walk up a certain hill, they end up with joint pain, they can modify their behavior before the logs start jamming the arteries.
Empowering the patient to understand their own physiology is the ultimate goal. When individuals develop these efficient coping mechanisms through self-awareness, they can actually manage their condition in an outpatient setting.
Keeping them out of the ER.
Right. They avoid the trauma and organ damage of frequent emergency room visits, allowing them to live close to normal lives.
Wow. So what does this all mean? We've traveled from a single water-hating amino acid to the hyper-filtering salty machinery of the kidney. We've explored accidental cancer cures, drugs that mimic the womb, and finally the profound power of a simple daily journal.
It's quite a journey.
It really is. Treating sickle cell disease isn't just about changing the microscopic shape of a red blood cell. It is about supporting the entire human system, especially those hardworking kidneys fighting a silent battle day after day.
It is a lifelong system-wide war. And I want to leave you with one final thought, based on a subtle detail buried in the research regarding the accidental cure we discussed earlier.
You mean the stem cell transplant?
Yeah. Hematopoietic stem cell transplantation is considered curative for the blood disorder. It gives the patient new, healthy red blood cells.
Right.
However, the source explicitly notes that, ironically, the harsh conditioning regimen required for the stem cell transplant, the chemo and radiation, can actually predispose patients to severe renal disease in the long run.
Wait, wow. So you cure the blood, but the process of curing it essentially guarantees the kidneys will take a massive hit down the line.
It creates this awful paradox, which raises a profound question about the future of genetic medicine for all of us.
What's that?
If our ultimate cutting-edge cures for complex diseases simply trade one form of organ strain for another, are we entering an era where curing a disease is really only step one?
Oh, I see what you're saying.
Will a whole new frontier of complex post-cure organ management become the reality of modern medicine?
A completely new set of murky diagnostic waters to navigate. Definitely something to think about the next time you see a headline announcing a medical cure for anything. Thank you for joining us on this deep dive.